Okay, hello everyone. Let's go ahead and continue with the modulus function. This is part 2. Now before, what we said is that we had the square root of x being x squared being equal to the absolute value of x. What we want to do now is we want to actually take a look at what that looks as a function. So in other words, if we were to go ahead and call the modulus here a function, so in other words f of x is equal to the absolute value of x, how do you actually go about graphing that? Now what we're going to have to do is we're going to have to introduce something called the piecewise defined function. Now the reason for the piecewise defined function is because we want to go ahead and write this as a function that doesn't involve the absolute value. So notice that if we go ahead and take a look at this right here, it says that if x is greater than or equal to 0, then the function absolute value of x is equal to x. And if x is less than 0, then the function f of x equals to the absolute value of x is actually going to be the same thing as the opposite of x. So notice that the reason why this is called a piecewise defined function is that basically what's happening is we're taking the domain and we're splitting it into parts. And for each one of the parts, you have a particular function. Okay, so notice that we're splitting this about the value 0. And we're going to associate a function with each one of the parts of the domain. So let's just go ahead and take a look at this now. I'm going to go ahead and draw this here. It says, what if we just looked at f of x equaling this part, the piecewise defined function for the absolute value of x. Now what I'm going to do here is I'm going to take a look at how you need to, I'm going to look at this as the way that you need to read this. It says if x is going to be greater than 0, then the function x, f of x is going to be equal to x. Okay, and I'm going to be using these green symbols here to go ahead and show you what that is. So pick any value that's greater than or equal to 0. So 0, 1, 2, 3, 4. You could pick anything so long as it's greater than or equal to 0. And I'm going to graph the function f of x is equal to x. So notice that that is the graph of f of x is equal to x. Now, that's only for all the values of x greater than or equal to 0. What about all the values of x that is less than 0? So what I'm going to do is I'm going to use red values for that. And if I go ahead and actually substitute any value of x that is less than 0, notice in other words it's a negative value, then the function that I'm actually going to be graphing is the opposite of x, which would then make it positive. So therefore all the negative values become positive values, which is the same thing as the absolute value of x. So notice that what I have here, notice that here I have an open circle at 0 because it cannot be equal to 0 there. But anywhere else less than 0, I'm going to have a positive value because all of these negative values will become positive values. So what I have now is when I put those two together, I come out with the absolute value function. So this is what the absolute value function looks like. It looks like a V. Okay? So what we're going to have to do then is we're going to have to practice actually determining how to write modulus functions without actually using the absolute value signs. And the way that we do that is again by using the piecewise defined functions. So this is how we're going to go about doing it. Let's say, for example, we want to go ahead and say y is equal to the absolute value of x minus 2. Now, if we wanted to go ahead and write that as a piecewise defined function, being that I know that it is an absolute value, I'm going to basically split it up in this way. Now, notice that what happens then is that anything here goes here and here. And anything here becomes a negative there, and the same value of x goes there. So notice that everything in between the absolute value bars is x minus 2. So what I'm going to do then is I'm going to say y is going to be equal to x minus 2, right? Because that's the part that's between the absolute value signs. If this part which is between the absolute value signs is greater than or equal to 0, it's the opposite of whatever is inside is between the absolute value bars if that part which is in between the absolute value bars is less than 0. So I'm going to simplify it now and just say that this is x minus 2 if x is greater than 2 because I'm just solving for x. Or it's going to be the opposite of x minus 2 if x is less than 2. Okay, so there you go. That's how you can go ahead and change what is a modulus function into its equivalent piecewise defined function. Okay, let's take a look at another one here. That was f.16a. Let's take a look at a different type of question that's being asked for in f.3. This is 3a. It says, if you wanted to solve this graphically, the absolute value of 2x minus 3 is less than x. How would you do that? Well, the first thing that we need to do is we need to go ahead and actually take a look at f of x here, and take a look at g of x there, And what we'll do is we'll analyze those two functions separately on the same graph and then look for where f of x is actually less than g of x. Okay, so let's go ahead and do that. I'm going to erase this here, and use this as our graph to solve this particular problem. Okay, I've done some of the preliminary work here. I've taken f of x is equal to 2x minus 3, and I've written it as a piecewise defined function. Okay, so I know that f of x is going to be equal to 2x minus 3 if x is greater than or equal to 3 halves. Okay, so here's where 3 halves is. It's 1 1/2. It's right there. Let's go ahead and use this in green. Okay, it's right there. Okay, and then it's going to be equal to negative 2x minus 3 if x is less than 3 halves. Okay, and so what I know then is it's going to look something like that. It's going to be that V shape again because it's going to be a modulus function. Okay, now I'm going to go ahead and also take a look at this function g of x, which we know is just going to be x. So if I go ahead and draw that, then this is what that function looks like. And then of course it continues down this way. Okay. Excuse me. That's g of x. Okay, now what we want to try to do here is we want to get an idea of where this function looks like, what f of x looks like. Now it says if x is greater than or equal to 3 halves, if it's greater than or equal to 3 halves this way, where does f of x equal g of x? Now we know that g of x is always going to be the same, it's always just going to be x. But f of x is actually going to be this part, the 2x minus 3, because we know that we're dealing with x values that are only greater than 3 halves, greater than or equal to 3 halves. So if I solve for this here, subtract 1x from there, so that's just x, move that over there, so x is equal to 3. So when x is equal to 3, it intersects. So those two functions intersect at that point. Okay, so now if x is less than 3 halves, where does f of x equal g of x? Well, if x is less than 3 halves, I know that f of x is actually the opposite of 2x minus 3. That has to be equal to g of x, which of course is still x. And if I solve for this, now I'm going to go ahead and just multiply both sides by a negative. If I move that negative x onto the, if I add x to both sides, I get 3x is equal to 3, so x is equal to 1. So it's looking like that. So this function looks something like this. Oops. Okay, anyway. It looks something like that. Okay, that's a little bit better. Okay, there you go. And this is actually f of x. Okay, so the question then becomes, is when is f of x less than g of x? And when is f of x less than g of x? Well, values for f of x being less than g of x, well, we know that it's actually equal to each other here. So it's from 1 all the way to 3. And anywhere between those two, but not including 1 and 3, you know that the value of f of x is actually less than the value of g of x. So the solution for this one here is going to be 1 to 3. Okay, or if you wanted to write it this way, you could. Okay, so that's how you could go ahead and graphically solve this particular equation, inequality here, that involves the modulus function. Okay, and you can do that by actually changing the modulus function into a piecewise defined function so that you can graph it. Okay, so we'll take a look at the modulus function part 2. Let's see if you have any questions the next time that we meet. Okay, good luck. See you next time. Bye-bye.